Obviously, when you're spraying thermal spray, you have to find a way to melt it, right? How are you getting the electricity to the gun to melt the metal, and how are you protecting the operator from that?
Yeah, well, that's a great question. And in this particular picture, you can see there, it's a coaxial cable. It's called coaxial because it does several things at the same time. It carries the electricity that melts the wire. It carries the actual wire that you're taking there, and it carries the compressed air used for atomizing it. So it's called a coaxial cable because it's doing that simultaneously. So in that picture, you see the red cables there. That's the actual coaxial cable. And that's draped over the operator's shoulder. That particular unit that he's spraying can carry up to 450 amps of DC current. So you don't want that hurting the operator, obviously. So this is where the wire starts. This is what's called the wire feeder. And the wire's on those two spools on the left side of the photo. And the right side is what's called the wire feeder. So the wire comes off that spool and it goes through some drive rolls and it gets transferred to the coaxial cable. So this is the actual wire drive rolls. And you'll see in the center there, it says the consumable feed wire stock. That's the actual wire we're going to melt. And that brass fitting on the left-hand side, that is the one end of the coaxial cable. And that is what connects the wire to that cable that takes it into to the operator. So this is that coaxial cable. And you see on the right-hand side there, you recognize that same brass end. That's what's sticking into the wire feed unit, and the wire goes down the center of that. The brass fitting there itself is what carries the electricity to it. It's inside that cable also. And then you'll see that there's two O-ring grooves that seal that inner chamber. And there's holes in that inner chamber, and there's compressed air that flows through that cable in a sealed manner. And this is actually the other end of that cable that goes into the torch itself. So that green liner, the green tube on the right-hand side, is a polymer liner that the cable runs through. And that has a little bit of lubricity to it, so the wire doesn't hang up in there. It also actually acts as a seal. And what it does is, when this cable is finally assembled, you'll recognize those two O-rings and the holes again. This is on the other side. So that compressed air flows on the inside of that cable to keep the cable cool. It also supplies air to the torch itself to do the atomization and to keep the actual air tips cool. This is the cutaway view of that same part. So you can see the O-ring grooves there. You can see that green liner. If you notice, that green liner is compressed. And the purpose of that compression is so all the air flows along that liner inside the cable, and it only has one way to go out and only has one way to come in on each end. So it keeps that compressed air flowing through the cable. Again, if you're carrying 450 amps of current, cables get hot. They get some heat to them, so you have to be able to keep them cool. And then in the center of that green unit, that's where the wire comes through and goes into the torch. And you see, this is the actual torch. You see there's 5 tubes there. That very center tube is also a compressed air tube. There's actually some auxiliary air that comes into the torch from another fitting. But also the air that was in the coaxial cables comes into that torch body, and that all adds up to be the air that's used to actually atomize the wire. The next 2 tubes from the center, you can see on the left-hand side, that's where the wire's coming out. And as that wire comes out, and those 2 wires touch, that's where the arc occurs. And that electricity for that arc is carried inside that coaxial cable along it's actually a conduit on the inside, electrical conduit on the inside. And the outer 2 tubes, they're compressed air also. That helps shape and atomize the actual molten metal. So the coaxial cable is a critical part of this total system. It's the interface between the operator and the electricity and the compressed air and the wire, and it's how you can guide that all and get into the spot where you really need it the most.
My knowledge of coaxial cable comes from like cable plugging in the back of my TV. You know, where's the coax cable? Like that's where I'm at. I couldn't imagine the amount of energy and power being surging through and operating that. Not only is there something unbelievably dangerous coming out of the gun, obviously there's a push now for automation in a lot of these processes. I couldn't imagine the stress of just being a person trying to operate that. Not only the time that it would take to spray something, But the dangers of being on the job, that's got to be a big relief, I think, of a lot of automation processes moving forward.
Well, it certainly does. And in defense of the process, this is DC current. So there's a low risk of the operator getting electrocuted. That's not the case. But there's a lot of energy in there that can create a lot of heat. And I'd like to show that a little bit. So you're right in that the automation reduces that. There is a risk with the heat, and you want to be careful with it. You see the bottom part of the picture, there's like two brass blocks, and there's two bolts there. That's called a fusible link. And that's capable of carrying 500 amps of DC current. Well, you got to make sure these fittings stay tight and the connections stay tight. You'll see that on that photo, that block has a little bit of corrosion on it, has a little bit of material missing. That's because that was not tight. And what it was allowing it to do is actually get some electrical heat going on there, which caused corrosion from the heat and the electricity. And you'll see between those two blocks are those three thin plates. That's the fusible link. That's the safety feature in that if you get a dead short, those things there will actually melt. That's the cable that connects to the top of the fusible link. And you can see that the dark colorness there on the plate there, that's oxidation that occurred from the heat that was being generated from a loose connection. Now, if it gets too loose, I'll show you what can happen now. We get what we call a meltdown. So now if you have the loose connection, you don't take care of it, that much heat generates that starts melting things. So you see that fusible link now doesn't look like it did in the previous picture. And if you look at the bolt that was holding that down in the next picture, we actually melted that brass bolt. So that's how much heat was generated with a loose connection. So again, it's a safety thing. We want to make sure all the connections are tight. And if you follow all the procedures and the processes and the safety precautions, it's a very safe operation. But if you don't follow them, you can have some risks here and some hazards that we don't want to expose our operators to.
What's the course of action here to salvage what you have here? And I mean, I think you just started on it, but yeah, it looks daunting.
Yeah. Listen, in this particular case, this was actually my demo unit. So I demonstrated to myself how critical this is. So one of the bolts got loose and it started heating up. And what got damaged was the actual two cable ends and the bolt. And we were able to salvage this fusible link. We took it apart, cleaned it all up, put new bolts in it, and we were able to salvage it and keep running the demo. Eventually, we replaced the whole fusible link, but we used it to get through the demo we were doing.